All right, guys, we're going to talk about section 3.5 today, which is transformations on graphs. And we're not going to draw a lot of graphs here. We're going to look at a lot of equations and be able to tell what's happening to the graph of that equation or that function or the parent function based on what's happening in the equation out of that. So learning a little bit of theory here. So what we start with is y equals f of x. This is what we're going to call the parent function. And that parent function may be like an x squared, a quadratic. It may be a cubic. It could end up being a absolute value equation. But the parent function basically means the most basic uh, style of that problem. So if we're talking about a quadratic, the most basic would be x squared. If we're talking about an absolute value, the most basic would be just the absolute value of x. Something that's the parent function. So it's the most basic of that type of function. And what we're going to talk about are the transformations that you can see based on some very simple ideas that if you latch on to this idea that anything that happens on the outside is vertical, and anything that happens on the inside is horizontal, that'll help you keep these things kind of separate and know which one's which. So anything happening on the outside of that parent function is going to be a vertical movement, whether it be a reflection across the x-axis or something like that, or it might be shifted up or down. And then anything that happens on the inside of that parent function. So easy one to think about here is the absolute value function. Outside of it would be outside of the absolute value marks. Inside of it would be in there with the x. So if something's happening on the outside, it's going to move it vertically. If it's happening on the inside, it's going to move it horizontally. And if you'll think about those things and keep that at the forefront when you're looking at an equation, it'll help you differentiate between what's happening on a function. So let's just get some theory out of the way first. And let's talk about shifts. We'll start with a vertical shift. A vertical shift is going to take the parent function, whatever it may be, and add something on the outside. So example of that might be y absolute value of x plus 3. That shifts it up 3 units. If it were absolute value of x minus 4, that shifts it down 4 units. So what it takes is, what's an absolute value graph look like? It's the V. It's one of your answers on the quiz, I hope. That V shape. And so originally it starts at the origin. If it has the plus 3 on the outside, it doesn't change how wide or skinny it is. It just picks it up and moves it 3 steps up. If it has a minus 4 on the outside, it just takes it from 0, 0 and moves it 4 steps down. So that's what the vertical shift on the outside does. So adding or subtracting something on the outside is a vertical shift. All right. And then a horizontal shift is going to move it left or right. And what that does is takes the parent function, and instead of doing that plus or minus k on the outside, it's going to, if you add something on the inside, that's going to move left. If you subtract something on the inside, that's going to move right. Okay. So again, if you take the absolute value equation, the plus 4 is going to be left 4. The minus 4 is going to be right 4. Okay. Plus on the inside is left. Minus on the inside is going to be right. Vertical shifts, if it's a plus on the outside, it's going to be up. If it's a minus on the outside, it's going to move down. That it's the opposite sign from what you would think it would be for the horizontal. Anything happening on the inside is kind of backwards. Seems like anyway. All right, so we can shift that, just pick it up and move it up, down, left, right. We can put them together. We're going to do some examples in a little bit where we put it all together and try to decide what's happening. But then we can take that original function and we can do a vertical stretch. And you guys may be maybe show my age here. Did y'all ever play Silly Putty when you were a kid? I'm still a kid. All right. I like my kids get Silly Putty. I like it because it's fun to play with. I grew up playing Silly Putty. Did you ever take it, mash it out real flat, and then get a newspaper or a coloring book or something like that and mash it down on there and then peel it off? When you do that, what happens is the ink transfers to the Silly Putty and it takes the picture off of the page and puts it on the Silly Putty. And then what you can do with that Silly Putty is then, like, if you put that down on a picture of maybe like Charlie Brown or something like that, and pull it back up, you got a picture of Charlie Brown there, and you take that Silly Putty, you can pull it like this, and what's it do to the picture? Stretches it out, makes it look what? When Charlie Brown's got that big old round head, you all know what Charlie Brown looks like. When you stretch it this way, what's it do to his head? Slims it up, makes it skinnier, right? That's what happens to the picture of the graph when you do a vertical stretch. And the way the vertical stretch looks in equation form is you're multiplying the outside of the parent function by some number, and that number, to be a vertical stretch, has got to be bigger than 1. Okay. We'll stick with the idea of the absolute value graph. If I multiply the absolute value of x by 3, it still has the V shape, but it stretches it up and it makes it skinnier looking. That's what multiplying by 3 on the outside does. So multiplying by a number bigger than 1 on the outside is going to be a vertical stretch. Now, there's a thing called a vertical compression. It looks the same. You got a number multiplied on the outside. The difference is the size of that number. To be a vertical compression, you have to be multiplying by something that's between 0 and 1. What kind of numbers are between 0 and 1? Fractions, small fractions in fact, like 3/4, 1/2. Okay? Same idea, you got the picture of Charlie Brown, and let's say our Silly Putty's thick enough that it'll stand up on its own. So we set it up on the desk, and then if you press it down, what happens to Charlie Brown's perfectly round head? It does this, right? It flattens out, and it looks like it gets wider. So when you compress vertically, it looks like the graph gets wider. That's what it looks like is happening. So a vertical compression and a vertical stretch, equation-wise, the multiplication happens on the outside because that's a vertical movement. To compress it vertically, stretch it out like this, that's a Y movement, a vertical movement. So it's multiplying on the outside. Compression, the same way. You're changing the Y values, making them smaller. And you're multiplying by a small fraction or smaller decimal on the outside. So multiplying on the outside is going to be a vertical stretch or a vertical compression, and it depends on the value that you're multiplying by. That number in the front, if it's a big number, then or a number bigger than 1, it's going to stretch it. If it's a number smaller than 1 but bigger than 0, it's going to compress it, multiplying on the outside. Okay, so if there's vertical stretches and vertical compressions, there are also horizontal stretches and horizontal compressions. And the way the equation works, let's do a horizontal stretch. You're going to multiply on the inside. A horizontal stretch, though, to get it to stretch horizontally, if you took the silly putty again, got Charlie Brown's perfectly round head, and we stretch it horizontally, what's it going to do? It's going to get it wider, right? It's going to look kind of like it did when we did a vertical compression. So when a vertical compression, our numbers had to be between 0 and 1. Same thing with the horizontal compression or horizontal stretch. Horizontal stretch and vertical compression, the number that you're multiplying by has to be between 0 and 1. Okay? And ideas think about, okay, vertical compression squishes it down, makes it look wider. Horizontal stretch does the same thing. So we know the number that you're multiplying by has to be the same kind of number. A horizontal compression equation-wise, you're still multiplying on the inside, but we're multiplying by a number bigger than 1. Okay? Horizontal compression takes Charlie Brown's perfectly round head, and when you press it in from the sides, it takes his head and squishes it and makes it look skinnier. Right? Same way that a vertical stretch does. So our A value has got to be bigger than 1, but it's multiplied on the inside to make it happen like that. So when you look at the graph of an equation, the look of it may be very similar, but where the actual math is happening helps you decide whether it's a vertical stretch or horizontal compression. Because the look is the same, but the equation and where things are happening at tells you which one of those is happening. All right. And then the last things that we have with our types of transformations that we're going to deal with are reflections. And a reflection across the x-axis. And then we'll do a reflection across the y-axis. It's weird that we're at this spot. I just went over this with my geometry class last week. Talking about transformations of geometric figures. If you reflect across the x-axis, what changes? Say it louder. The y values are what changes. The x values don't change. So you're reflecting across the x-axis. You're taking a picture that's up here, and say my arm is the x-axis. And when you take that picture and move it down here, the y values change, but the x values stay the same. So when you see a reflection across the x-axis, that's a vertical movement. So the equation has the negative on the outside. If you reflect across the y-axis, and that's the vertical one, we got a picture over here, and we reflected across the y-axis, what changes? The x values. The y values don't change. So our equation has the negative on the x's. Okay. So what we're going to do is we're going to take some functions, and we're going to first write the new function based on what transformation they tell us to do. And then we're going to go the other direction. We're going to get a function that's been transformed, and we've just got to look at the equation and tell what happened to it. Did it get vertically compressed? Did it get shifted left, right, up, down, that sort of thing? So let's start with this one, sample A. Here's our function. We'll start with just the x squared function. We all know what that looks like. To begin with, we know that the picture of the quadratic is that U shape. That's the normal parabola shape. Starts at 0, 0, goes up in both directions, or on both sides there. Domain from negative infinity to positive infinity, range from 0 to infinity, that sort of stuff. We know that about that. So the first problem we want to do, we're going to do several parts here. We want to take that function and let's shift down 5 units. What would be the equation if we were to shift that down 5 units? X squared minus 5. Absolutely. What does that look like on the graph? We take that U shape and we just move it down 5 units. That's all it does. You could graph that. You graph the original, graph that new equation. You'd see that shift happening. It is that easy. Don't overthink this, as it really is. So as we go to each problem here, go back to the original. Okay. We're not building on this. We're not doing one transformation, then the next one on top of that. We're starting back over every time with y equals x squared. All right. So let's go left 2 units. How do we do left? Which one is it? Plus 2 on the inside. And then it's still squared because it's the quadratic. It's x squared, right? So on the inside means you do that to x. So x plus 2 is going to move us left 2 units. Okay. And that would be our new graph. And again, you can check that by graphing the original and then graphing that new equation with your calculator if you wanted to. I'll show you that. Y equals, I'm going to clear out what I had there. I'm just going to graph the original. The blue one you see on my graph is going to be the original. The other one is going to be parentheses x plus 2 squared graph. There's our original, and then there's left 2 units, the red one. So that lines up to what it said to do. Okay. All right. So let's put it together. Let's do up 6 and right 7. A little bit of both here. All right. So what goes? What in the parentheses again? Say minus 7 because we're moving to the right this time, and then on the outside the up 6 would be plus 6. X minus 7 on the inside, and then plus 6 on the outside moves it to the right 7 units and up 6 units. Job. Let's do a vertical stretch by a factor of 4 and down 3 units. All right, so vertical stretch of the x squared function by a factor of 4. That means we're going to be multiplying by 4 somewhere. Is that 4 on the inside or the outside? Outside. So it's going to be 4 x squared, and then down 3 units would be minus 3. Let's do a horizontal compression by a factor of 6 and up 8. Horizontal compression. So we know that's going to happen where? Inside. So we got to have parentheses by a factor of 6. And then plus 8 on the outside there. It's up 8 units. If it said horizontal stretch, what kind of factor does it have to be by? Yeah, small fraction or small decimal between 0 and 1. So be careful of that. Do one more with that same function. Let's do a reflection across the x-axis, a vertical compression by a factor of 1/2, left 3, up 6. A lot of stuff happening with this one. All right, so where's this reflection across the x-axis? What's it do? So a negative goes where? On the inside or outside? Outside. A vertical compression goes where? Vertical compression goes on the outside. And then moving to the left 3 will be x plus 3. And up 6 would be plus 6 on the outside. Lot happening with that one. But again, reflection across the x-axis is a vertical movement because it's moving up and down. So that's on the outside. So that's where the negative goes. A vertical compression, that's going to go on the outside. So that's why we put a 1/2 outside. Left 3, that's left and right. That's a horizontal movement. So that happens on the inside. And then the up 6 is vertical. So it happens on the outside as well. Okay, so they don't get much more complicated than that one as far as doing a problem this style. Okay. All right, let's go the other direction and take a function and describe the transformation. So example B, describe the transformation on f of x equals the square root of x. I'm going to do 2, 3 of these. So the parent function is square root of x, and then this one has the square root of x plus 3, and then a minus 6 on the outside there. So what transformations are happening to that function? Left 3, down 6. And it doesn't matter which order you list those. That if you wrote down 6, left 3, that's fine. Do the same thing. That one. Okay, reflect across the x-axis. Then a vertical stretch. 3. You can write by a factor of 3 or just by 3. I'm pretty loose on that. And then what's the minus 5 on the inside? Right. Again, technically, it does not matter which order you write those answers in. Do one more of these. reflection across the y. Where's that coming from? That's right. Yeah, that negative on the inside with that x there is reflect across y-axis. What else? Left 7, up 8. Good job. Pretty easy thing here. Any questions about the first two little things that we've done here? All right. Last thing, I think this is the toughest part, even though it seems like it should be the easiest. This may be the part that gets kind of gets messed up the most of anything in this section, and that's where you've got to take one ordered pair and apply transformations to that. And so let's say if 2, 6 is on the graph of f of x. Doesn't matter what function f of x is. F of x could be the x squared function. It could be the cube root function. It could be x cubed. It could be, the absolute value. It doesn't matter. We're just looking at this point, 2, 6. So the x value is 2, the y value is 6 out of that. What is the ordered pair after this transformation? Y equals -3 f of x minus 1. All right. So the key to doing this type of problem is not plugging in x. I know that's been the focus of a lot of things that we've done in chapter 3, is you took that 2 and you plugged it in. Don't do that here. Okay. What you want to think about here is the same things that we just did in example B. What transformations have happened to f of x based on that equation? So let's talk about the transformations that have happened there. Okay, so there's a reflection across x-axis, vertical stretch by 3, and then what else? To the right 1. All right, so we're going to take those transformations and apply them to that ordered pair. Okay, so if it's going to reflect across the x-axis, what part of that ordered pair changes? The y value. So the 6 is going to become -6. And then the next transformation y'all said was vertical stretch by 3. So a vertical stretch changes what? The y. It's a vertical movement, so it's going to change the y value. So we've got -6 right now after the reflection across the x-axis. Vertical stretch by a factor of 3 does what to the y value? It multiplies it by 3. So what's -6 times 3? -18. And then right 1 moves what value? It's going to move the x value. The y value is still going to be at -18. The x value, if it's at 2 right now, right 1 would be at 3. So the new ordered pair would be at 3, -18. And again, we don't have the original function. We don't know what the original function was. It doesn't matter. We're taking an ordered pair and we're applying these transformations to that ordered pair. So again, vertical movements are going to happen to y. Horizontal movements are going to happen to x. Okay, anything vertical is going to happen to y. Anything horizontal is going to happen to x. Let's do another one. Same ordered pair, same rules. What's the ordered pair after this transformation? Maybe something it may be easier here. But again, same idea. What transformations are happening? Left 4, down 8. So we're taking the ordered pair 2, 6 and moving it left 4 and down 8. So what's left 4 from 2? -2. And then down 8 from 6. It'd be a -2 as well. So the new ordered pair is at -2, -2. Okay, again, don't plug in the X, because that's the most common mistake there. Look at the transformations that are happening and then apply those to the ordered pair. Okay, look at the transformation that's happening and apply those to the ordered pairs. So really, really basic ideas here in theory about the idea of this whole section is not necessarily that you use the calculator to graph a lot with, even though that's helpful sometimes, but it's that you learn how to look at an equation and tell what happened to the original function just by looking at it. So you get in the lower level maths, we talk about number sense and being able to do math with numbers without using the calculator. When we get into upper level here, we're thinking about function sense and being able to look at a function and tell what's happening to it or how to work with it just based on looking what the equation has. So 1 through 65, again, the odd ones.